Alright, it's streaming. Can I see my face? Not yet. I can now, and can I hear myself? Hello? Can I see my face? Awesome. So we're going to turn this up a bit more. Hello, hello, hello. Awesome. So we're going to turn this up a bit more. Hello, hello, hello. It's not bad. Okay, cool. Right. Let's do this. Sorry for the tunnel vision there. Okay. So, as always, let's start with a sip of coffee, actually. So, let's start with a Duolingo lesson, but also let's start with I've been away because of house stuff, and also because I've been watching Manolis Kallis's lectures on exactly what I want to do. So, biological engineering, life science, um, you know, creating AI that will do stuff for us, for me, and it's been really important to just watch some of those videos. I haven't got very far through. Actually, I left a tweet to him to say I'm going to binge watch them, but it hasn't worked out that way because actually, um, they're quite information rich. So, uh, taking some time over them has meant that I've absorbed them a bit better. It's cool as well because I did a bit of AI stuff beforehand with PyTorch and a couple of the equations that work alongside with it. So it's been really interesting to have a kind of subtle insight into what on earth he's speaking about. Um, Having said that, let us do our Greek lesson. Yay! Let's see if I can fit. Oh yeah, I might have done a couple whilst you're gone, but not a lot. Mostly been doing the Finnish stuff. All right, so hopefully you can hear this. Just look at the tool. Okay, I don't think it says anything. So select the correct characters for NA. Well, we know that V is the end, so that must be that. Nah. All right. Match the pairs. An would be an. Ro, and then an A would be that. Select the correct characters for an. Match the pairs. Ro, ro, na, na, an, an, ro. Cool. The water. Cafe Nero, so to nero. Nana. That means Nana? Nana. Nana means. Yikes, I don't know. It means Nana. Okay, fine. Don't know what that means. Mark the carrot. Well, I guess it would be. Oh, I've done it again. I need to do the keyboard settings. Always forget this. No. Yes, that's right. That's right. That's right. That's right. All right. So Mark would be mar, like that. Oh, it'd be helpful if I actually typing in there. Mark to carotto. Nice. Nana. Whoa. Nana to nero. Nana to nero. Nana, the water. Mark to carotto. I don't know if there's two. That's gonna be wrong. Oh, it's right. Wow. Okay. Awesome. Sure, why not? Let's get one of those. Okay. Right. I feel like I should do more, but let's not. So I have to remind myself because it's been a long time since I've actually seen this stuff. But I remember we were learning about periodic table, like atomic, uh, like the the atomic mass, the atomic number, the calculation to get the atomic mass, which is, I have to remind myself, it's the electrons on the outside and the neutrons are neutral, so it's the protons. There's an equal amount of protons and electrons, and uh, the atomic number is oh sugar. Yikes, Scoob. No, I do know this. I know this. It is the atomic mass is. Oh, that's right. It is simply the account of protons, and then the to find out the atomic mass. If you have electrons or protons, you have to. Uh, no, I can't remember. Ha! I tried. I tried. Uh, let's just look that quickly up. So get the count. No, what does the atomic mass? Yeah. Uh, it is the common 16 neutrons, atomic mass of 12. Ah, it's neutrons and protons. Let's see if I've got this documented. I bet I have. It'll be in here, 6. Oh, excuse me. I always do this when I'm tired. This is just the worst way of learning, but yep, there's always equal protons. Oh, this is a bad diagram. um, it's always an equal amount of protons and electrons because there is a balanced charge unless it's an isotope. Yeah, something like that. Okay, let's just click through to this. Khan Academy, the one and only. I'm just going to review like stuff I've done, and then I'm going to set a goal for today of something. I think I'm hankering on wanting to know how to draw a chemical formula, and I think it's important because I want to start to discuss my ideas with people, and in order to do that, I need to know how to communicate with people about chemistry. And I also identify, like, look at some like white papers and identify where flaws are, and I don't, like, if you're a programmer, you do pull requests, and I think I'd like to try and join in that with the scientific community for biology and chemistry. I think it's a good entry point because I'll start to notice what other people do, their mistakes, their success, their successes. That's the word. Words. Hello. Right. Atoms of each element contain a characteristic number of protons. In fact, the number of protons determines what atom we are looking at. E.g., all atoms with 6 protons are carbon atoms. The number of protons in an atom is called the atomic number. The number of protons in an atom is called the atomic number. Step 1. In contrast, the number of neutrons for a given element can vary. Forms of the same atom that differ only in the number of neutrons are called isotopes. Cool. Together, the number of protons and the number of neutrons determine an element's mass number. Ah, I was off. Okay, so it's neutrons and protons. Fair enough. If you want to calculate how many neutrons an atom has, you can simply subtract the number of protons or atomic number from the mass number. That's right. Okay, it's all coming back to me. Hopefully, it's coming back to us. Okay, maybe. So, number 1, I think that's very important to know. Number 2 is, we're probably on number 3 now, I don't know. We were learning about how the chemical formulas are laid out. We learned about this kind of cool wedge scheme whereby, or wedge model, wedge drawing, that denotes like 3D structure, and you've got like different a wedge and a dotted wedge or something like that that notes if it's up or down or something like that. That was a skeletal formula, was it? I think so. Skeletal formula. Yeah. Oh yeah. It's probably in here actually. A little bit zoomed in, maybe. Oh yeah, that's why I'm zoomed in, because you can't see it otherwise. You not sure this is what I wanted. Skeletal formulas. It is that one. It has these funny lines coming out of it. Yeah. Okay. So we learnt that. We learnt. Uh, we actually looked at like a BBC bite-sized thing for GCSE about reactions, and that kind of made sense. What else did we learn? Periodic table, periods, groups. This is stuff that I can always look up, but it was good to have some kind of formal knowledge of it. I think we've come up to the end of what I've learned, and we've got all the kind of pre parts, the episode 1 to 4, whatever it was, about CRISPR. So we've got all that kind of knowledge, RNA, gRNA, nuclease, nucleotides, which is the structure between the DNA. Yeah. And then what else? Common memory, do me proud. What else have we got? We've got one more thing. There's one more thing I learned, and it was oh, I can feel the neurons rebuilding now. Come on, search mechanism, do your thing. How do I how do I search for it? What did we do? We did the atomic numbers, protons, electrons. Ah, yes, 228 electron fields on the outside. There's like grouped into like these different fields, and there's 2, 2, 8, and then it gets more complex on the outside, I think. Yeah, okay, cool. That's good. That's good. So let's start this by saying episode 8, and we need to discuss what we want to learn. It's quite late, but I've got a hankering for the knowledge today, so I don't know how long this will go on for. It probably won't be that helpful for you guys to watch, but anyway, hello anyway. Yeah, just me at the moment, so all good. Right, what do I want to do? I want to write a formula for anything. So I need to start practicing that skill, I think. And the end result will be that I want to create a program whereby I can give the computer a chemical or two chemicals, and it should combine the two to make the reaction or something like that. And the reason I want to do that is because I want to be able to discuss with people that stuff. I think I don't want this to be too heavy on this. I just want to know the foundational part, because I need to start diverting back onto CRISPR. I need to start rerouting back onto CRISPR, and the reason I need to do that is because I need to start focusing on the AI part. There's a lot of stuff I'm totally happy to share live and online. I find learning some real focus stuff, whilst I know that people might watch me, a little bit difficult. So I think it's a good way to teach myself the skills for that. So I'll load up probably some Python, or maybe some yeah, most likely Python, and and start learning AI, I guess. Finally, these won't be as often as I'd hoped for, these videos, because I am learning on the fly from lectures as well, and I don't think it's right to just stream myself watching them. Although I mean, maybe I need to start using something like Twitter or yeah, Twitter to say what I'm actually doing whilst you can't see live videos. Okay. Okay, so let's write that down. So the goals are, whoa, the goals are 1. Start to focus in on excuse me, I know, looking at 2 chemical structures. No, start to focus in on looking at how reactions work. Focusing on how to describe chemicals in the diagram sense. Then I need to write a program. This would be a big job, by the way. Write a program. Well, I guess we need to first focus in on chemical reactions and how to know what will occur or what is needed to invoke reactions, figure out leftover matter, etc. Write a program that formulates a model for all of the above, simply to use for learning, and then swerve back onto, that's not how you spell swerve, is it? Swerve back onto CRISPR, DNA, nucleotides, etc. Using the above program, we'll play with these and then focus in on AI, where really the rest of most of this work is going to be. And then I need to start to, I think over that period, I will have to start to figure out what I'm going to focus on. I feel like I know what's missing in terms of the general science that is missing at the moment is how to catalyze the DNA sequencing with material to generate, like a 3D printer biology. I know that some group just recently did some kind of model creation using sequencing, but I think that's like cutting edge stuff. So I think that's where I want to go and like fill out that gap. And I also want to figure out, is it that I want to repair bones quicker or better, or is it that I want to repair people who can't walk, or do I want to think bigger? Do I want to focus in on adapting humanity to um, succeed when times are much harder on Earth, the atmosphere, or visiting Mars. You know, preparing generations who are more defended against all the kind of radiation or lack of oxygen, etc., like that. Um, yeah, I'm not sure what to focus on, but I know what my original goal was, and it's really feeding into more. So my original goal was to make a kind of exoskeleton thing that would help people walk, and I would study AI to drill into the spine and you know, with precision and interact with the the nerves and all that stuff, and then kind of grow itself into you using some DNA sequencing and some kind of biological computer to figure out what best role to play in your body. But then I start to realize that in the future, I doubt the body is going to be that important to us, considering its flaws on other planets. You know, we're evolved to live here, not somewhere else. So I think mostly we need to understand the brain, but I'm not a neuroscientist and I don't want to be one yet, at least. So I think that I think it all stems into this, which is to understand, you know, how to manipulate the DNA and to express yourself scientifically speaking for the wider community to start to acknowledge you exist. Wow, okay, 20 minutes of just talking, 22 minutes. Focusing on A. Okay, so start to focus in on how to describe chemicals in the diagram sense. It's a big task. Let's do it. Let's start. It's going to go on for a few episodes, of course. Let's take the most simple of things. Let's think of a cool chemical. What's a cool chemical? Let's take cannabis. Cannabis is cool, right? Everyone loves cannabis. Let's see, cannabis wiki. Uh, what does it contain? It's THC, isn't it? Something like that. Formula, chemical, chemical composition. That sounds good. Wow, I have a backache. That sucks. The main component of cannabis is THC, formed from decarboxylation of THCA. Raw leaf is not psychoactive because cannabinoids are in form of carboxylic acids. THC, alright, there's one, THCA. Formed from decarboxylation of THCA. Well, let's go for THC first. So there we are. And I want to be able to look at the formula, I want to be able to draw it. And then I want to say what happens if you add acid to THC, an acid, you know. Okay, let's just look at this again. Oh yeah, this is really cool. This really cool periodic table that we like. I think we'll keep that up still. That's fine. We can close that. We've got all this kind of stuff that we were learning, but I think it's probably a very slow route to what I want to do. So, but we know it's there. We know it's there, so that's good. And we can always, you know, if we get stuck, we can always go back at it. All right, cool. So starting with this, uh, tetrahydrocannabinol. Let's just break this word down. The etymology of cannabis. Ha! No, that's not what I wanted. I like this top part. Tetrahydro. I want to know what tetra means, so define tetra. Okay. That's not it. Etymology of tetra. Tetra tetragonal. Okay, this might be it. Okay, let's see. There's nothing particularly tetragonal of that. One of the structural categories to which crystalline solids can be assigned. Crystals in this system are referred to three mutually perpendicular axes. Perpendicular axes, two of which are equal in length. Yeah. Hydro, water. Is hydro water? I think it is. Etymology of hydro. Water. Cannabinol. Let's see what this means. OD traces the etymology to the New Latin botanical term cannabis, proposing from recorded the use of cannabis in the histories. Marijuana word. Specific drug was popularized by what does cannabinol mean? Crystalline, mildly psychoactive cannabinoid that is found in very small quantities as a breakdown product of THC and is believed to have sedative properties. So it'd be interesting, you know, because cannabinol, it says it's got sedative properties. I need to understand. Well, maybe I don't. I feel like it'd be cool to understand what effects different things have on biology of a human. Anyway, so something like the shape of water, and then this actual thing. THC is the principal psychoactive constituent of cannabis, although the chemical formula for THC describes multiple isomers. Okay, here we go. So let's study in on this. Let's get this in the bag. A subpage. No, don't do that. Weirdo. New page. Ah, there it is. Make subpage. No, it's not. That's what I just pressed. Make subpage. Oh my god, I'm not even clicking the right things. New page. Make subpage. That. THC. So I've chosen THC as it is a fun topic. Let's. I want to study its formula and understand how to play around with it. So number one, I guess, what are the components of this? Well, I can look at the periodic table. So it's got carbon. Looks like it's got 21 of those. It's got hydrogen. Looks like it's got 30 of those. Hydroga. And then it's got 2 oxygen. 2 times oxygen. Now, is there anything interesting about this? Well, I think what's interesting is that it says hydro, and we have something called H30O2. Now, is that coincidence? I think not. And then what else is really interesting about it is that it's a pretty boring mixture of ingredients to make such a to have such an effect on a body. That is very interesting, isn't it? Like there's just the 3 elements bound together in such a formation describe such a complex framework of um, of functionality. Okay, let's check this out. Isomer. In chemistry, isomers are molecules with identical molecular formulas. That is, same number of atoms of each element, but distinct arrangements of atoms in space. Isomerism Excuse me. Is existence or possibility of isomers. Okay, cool. Isomers do not necessarily share similar chemical or physical properties. Two main forms of isomerism are structural or constitutional isomerism. Constitutional, in which bonds between the atoms differ, and stereoism. This is stereo is solid, or like structure, 3D stuff. Stereoisomerism, or spatial isomerism, in which the bonds are the same but the relative positions of the atoms differ. Let me just read it one more time. Isomers are... Wait, how do you say this? Jeez, how do you say... No, how do you say... I think because Google has this now.
Isomers.
Isomers, alright, I wasn't being a noob. So isomers are molecules with identical molecular formulas. Let's look at this again. Describe multiple isomers. What is that trying to say? What is that trying to say? THC describes multiple isomers. Isomers are molecules with identical molecular formulas. Describes multiple isomers. The term THC usually refers to the delta 9 THC isomer with the chemical name negative trans delta 9 tetrahydrocannabinol. Like most pharmacologically active secondary metabolites of plants, pharmacologically active secondary metabolites of plants. Metabolites. THC is a lipid, a fat found in cannabis. Assumed to be involved in the plant's evolutionary adaptation putatively against insect predation, ultraviolet light, and environmental stress. That makes sense. That makes a lot of sense. Along with its double bond isomers and their stereoisomers, is one of only 3 cannabinoids scheduled by the UN Convention on Psychotropic Substances. The other 2 are dimethylheptylprion, dimethylheptylprion. Gosh, that's a big word. I can see some of it. Di too. Methyl, alcohol. I don't know. Methylheptyl heptaliprion. I don't know. How do you say? Oh, let's go. Let's go to Emma.
One of the great challenges in this world is knowing enough about a subject to think you're right.
Dimethyltryptamine.
Okay, dimethyltryptamine. Okay, let's break that word down. Etymology of dimethyltryptamine. Dimethyl. Oh, this is different. Tilperin. Tilperin. Dimethylheptylprion. Gosh. Let's try that again. That is not what I wanted, I have to say. Methylheptamine. Nope. Let's see if this works.
Dimethylheptylprion.
Huh?
Dimethylheptylprion.
That's not that helpful. That's not actually spoken, is it? Okay, well, okay, fine. Let's just do the etymology of it. It doesn't really matter how we say it. We'll call it Bob, I guess. Etymology of that Keith. I wonder if it's got it here. This is good. This is good stuff. This is what I need to look into. Okay, so how do we structure this? And so it says that this is structured like so. Now, why is that? So 21 carbons. Now, there's something about, if it doesn't mention it, it's because it's next to something or is assumed to be something. I remember something like that. Because there's certainly not 30 H's here. 2 oxygens, okay, and 1 is bound to a hydrogen. Okay, yes, this is exactly what I want. So I need to understand this properly, and this is a skeletal formula, I think. Yeah, it is. Yeah, this, okay, I remember this stuff. Cool. Alright. The skeletal formula, also called line angle formula or shorthand formula, excuse me, of an organic compound, is a type of molecular structural formula that serves as a shorthand representation of a molecule's bonding and some details of its molecular geometry. A skeletal formula shows a skeletal structure or skeleton of a molecule, which is composed of the skeletal atoms that make up the molecule. It is represented in 2 dimensions, as on a piece of paper. It employs certain conventions to represent carbon and hydrogen atoms. Yep, I can see that. Which are the most common in organic chemistry. An early form of this representation was first developed by the organic chemist Friedrich August Kekulé von Stradonitz, while the modern form is closely related to and influenced by the Lewis dot structure of molecules and their valence electrons. For this reason, they are sometimes termed Kekulé structures or Lewis-Kekulé structures. Skeletal formulae have become ubiquitous in organic chemistry, partly because they are relatively quick and simple to draw, and also because the curved arrow notation used for discussion of reaction mechanism and or delocalization can be readily superimposed. Okay, that makes sense. Several other methods for depicting chemical structures are also commonly used in organic chemistry, though less frequently than skeletal formulae. For example, conformational structures look similar to skeletal formulae and are used to depict the approximate positions of the atoms of a molecule in 3-dimensional space, as a perspective drawing. Other types of representations, e.g. the Newman projections, Haworth projections, and Fisher projections, also look somewhat similar to skeletal formulae. However, there are slight differences in the conventions used, and the reader needs to be aware of them in order to understand the structural details that are encoded in these depictions. While skeletal and conformational structures are also used in organometallic and inorganic chemistry, the conventions employed also differ somewhat. Terminology. The skeletal structure of an organic compound is a series of atoms bonded together that form the essential structure of the compound. The skeleton can consist of chains, branches, and/or rings of bonded atoms. Skeletal atoms other than carbon or hydrogen are called heteroatoms. The skeleton has hydrogen and/or various substituents bonded to its atoms. Hydrogen is the most common non-carbon atom that is bonded to carbon and, for simplicity, is not explicitly drawn. In addition, carbon atoms are not generally labeled as such directly, i.e. with a C, whereas heteroatoms are always explicitly noted as such, i.e. using N for nitrogen, O for oxygen, etc. N for nitrogen. Okay. Heterogeneous, I guess. Heterogeneous. Diverse in character or content, okay. Heteroatoms and other groups of atoms that give rise to relatively high rates of chemical reactivity or introduce specific and interesting characteristics in the spectra of compounds are called functional groups, as they give the molecule a function. Heteroatoms and functional groups are known collectively as substituents, as they are considered to be a substitute for the hydrogen atom that would be present in the parent hydrocarbon of the organic compound in question. Let me just reread that. Heteroatoms and functional groups are known collectively as substituents, as they are considered to be a substitute for the hydrogen atom that would be present in the parent hydrocarbon of the organic compound in question. Okay. So basic structure of a skeletal formula. As in Lewis structures, covalent bonds are indicated by line segments with a doubled or tripled line segment indicating double or triple bonding. So in this case, this is triple bonding, and you can clearly see that this is bound to this, this is bound to this, and this is bound to this. So it's line segments with the doubled or tripled line segment. So in this case, you've got like a double bond, and double bond. I wonder if this, so a triple bond is a chemical bond between two atoms involving 6 bonding electrons instead of the usual 2 in a covalent bond. So structure and AFM atomic force microscopy image of dihydrobenzoanilide, where benzene rings are held together by triple bonds. I can't believe that. Is that really what it looks like? It can't be. There's no way. Is that really what things look like? Whoa. chemical structure of triangular dihydrobenzoaniline. Horizontal elation, whatever that field thing was. Shows the STM stereo something topography measurement parameters. Oh my god. Sorry, I am actually blown away by that. I had not realized things actually structured like that. I assumed before, then I was led to believe that things weren't quite as simple as this. That is insane. That is so very evident. Okay, cool. Right. So, um, so this is interesting. There's actually 3 distinct lines here. I'm not quite sure if it's this or if it's this 3 lines. I'm guessing it's these because these are the bonds between the two. I think it makes sense. Okay. Likewise, skeletal formulae indicate formal charges. Likewise, skeletal formulae indicate formal charges associated with each atom. Although lone pairs are usually optional, see below. In fact, skeletal formulae can be thought of as abbreviated Lewis structures that observe the following simplifications. Carbon atoms are represented by the vertices, intersections, or terminations of line segments. For clarity, methyl groups are often explicitly written out as Me or CH3, while heterocumulene, I don't know what that means, hydrocarbon with 3 or more cumulative double bonds, while other double bond carbons are frequently represented by a heavy center dot. Okay. Hydrogen atoms attached to carbon are implied. Hydrogen atoms attached to carbon are implied. So let me just take a stop here, sorry. Hydrogen atoms attached to carbon are implied. So we've got 21 carbons are attached to hydrogen, 30 hydrogens. So that means I've got 9 missing. 876. So they are implied. Hydrogen atoms attached to carbon are implied. An unlabeled vertex is understood to represent a carbon attached to the number of hydrogens required to satisfy the octet rule, while a vertex labeled with a formal charge and or non-bonding electrons is understood to have the number of hydrogen atoms required to give the carbon atom these indicated properties. Whew. Optionally, acetylenic and formyl hydrogens can be shown explicitly for the sake of clarity. This is information dense. I'm just trying to get a little intuition first before moving on with the actual detail. 21 carbons. Let's have a look. 1, 2, 3, 4, 5, 6. These are hexagonal. Yep. Hexagonal, so that's 6 plus 5 plus 5. So it's 21. That's interesting. And then we got 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 21 sides for all hexagons. That is 6 plus 5 plus 5. And then we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 lines. Oh, actually, 4, 5, 6, 7, 8, 9 lines. 9 lines. 21 plus 9, 30. And then we've got 2 oxygens that are explicitly shown. 2 O's explicitly shown. So that's interesting, isn't it? So I think there's some comparisons here. 21, and then you got the 30 for all of them. Okay. And there's some like structure here, some 3D structure, because you can see this goes out into the X direction and into the X direction. And then you've got this other thing here. Now let's have a look. This is probably this. Then you've got this hexagon, sorry. Then you've got the second part and it comes off here. And there are 2 open bonds, something like that. But there is 3 here. Now, so I guess that's not how that works. Unless everything will have a bond and that's just a given. Okay, I think it's probably a better way of learning this. Learning skeletal formulas. Does this look heavy? It doesn't look so heavy. And I love that they've got this this language that draws it as well. Right. Okay. Let's do this. So this page explains the various ways that organic molecules can be represented on paper or on screen, including molecular formulae and various forms of structural formulae. Molecular formulae. A molecular formula simply counts the numbers of each sort of atom present in the molecule, but tells you nothing about the way they're joined together. For example, the molecular formula of butane is C4H10, and the molecular formula of ethanol is C2H6O. Molecular formulae are very rarely used in organic chemistry because they don't give any useful information about the bonding in the molecule. About the only place where you might come across them is in equations for the combustion of simple hydrocarbons. For example, C5H12 plus 8O2 combusts 5CO2 plus 6H2O. In cases like this, the bonding in the organic molecule isn't important. C5 becomes 5C. Oh, you can't see that at all, I'm so sorry. I'm looking at this here. So we've got this 5 here, okay. We've got 2 oxygens. Well, there's 2 oxygens over here. And there's, okay, let me just let me pull this apart a bit. So I think we skipped ahead a bit. I guess that's why it's a little bit difficult here. New page. And this is I don't know what this is. Let's try and figure this out. So we've got carbon. Let me draw this instead. We've got a 5. We've got a 5 here. We've got a 2 on the oxygen. We've got a 2 on the oxygen. So this is the whole thing here. We've got 8 oxygens. 12 hydrogens. This isn't 12 hydrogens. This is, yeah, what do the numbers mean? A chemical formula. So many adverts on that page. When we're balancing chemical equations, we need to know what symbols and numbers mean. When we are balancing chemical equations, we need to know what the symbols and numbers mean. When we write an equation for a chemical reaction, for example, Mg plus Cl2 chlorine, magnesium chlorine 2, each atom or ion of an element is represented by a chemical symbol. Yep, Mg is the chemical symbol for magnesium. Mg means one magnesium atom. Mg is the same as, one magnesium atom, okay. Cl means one chlorine atom. Cl2 means two chlorine atoms. Alright, okay, good. So the formula of a compound cannot be changed. The formula is shown by small numbers written after and a little below each element in the compound. KCl is an ionic compound. KCl means one potassium ion with one chlorine ion. The number 1 is never written. KCl is equal to K1Cl1. Na, sodium, 2 sodiums and 1 oxygen means 2 sodium ions with 1 oxygen ion. And it's an ion because they've attracted each other. Aluminium 2 and oxygen 3 means 2 aluminium ions with 3 oxygen ions. We shall look at 2 examples of unbalanced equations. You can balance any chemical equation by applying the rules shown in these examples. So click on the example below. The reaction of potassium with chlorine. When we are balancing chemical equations, we first need to know what the symbols and example 1 is the reaction between potassium and chlorine. So K, potassium plus chlorine, 2 chlorine, outputs to potassium chlorine. On the left side of the arrow, there is 1 K and 2 chlorine. The 2 chlorines in Cl2 cannot be changed, since Cl2 is the formula of chlorine. On the right side of the arrow, there is 1 K and 1 Cl. The reaction is not balanced because atoms are not gained or lost in a chemical reaction. The right side needs an extra chlorine. A big number in front of the symbol changes the number of elements in the formula that follow it. A big number in front of the symbol changes the number of elements in the formula that follows it. 2K means 2 potassium ions. 2Cl2 means 4 chlorine atoms. Two KCl means 2 potassium ions with 2 chlorine ions. Okay, to get an extra chlorine on the right side, we can put a 2 before KCl. The equation becomes potassium plus 2 chlorine becomes 2 potassium chlorine. Now the equation is balanced for chlorine, 2 on each side. But the equation has now become balanced for potassium. Yeah, there is 1 on the left and 2 on the right. To get an extra potassium, you can't see this, I'm so sorry again. To get an extra potassium on the left, we can put a 2 before K. The equation is now balanced. QK plus Cl2 equals 2Cl. On the left there are 2 potassiums and 2 chlorines. On the right there are 2 potassiums and 2 chlorines. Showing the 3 steps together, we have K plus Cl2 unbalanced for chlorine, unbalanced for potassium, balanced. When we are balancing chemical equations, we first need to okay. Example 2 is the reaction between lithium and oxygen. Lithium plus oxygen. Well, let's give this a try then. Whoa. How do I undo? Or whatever. So, in this case, Li, there's only one of them, right? And we're going to add O2. So the output must be O2, but we've only got one Li, so we need 2 oxygen. So we'll pull this one over to here. So now we've got 2 oxygen and 2 lithium. So I don't know where the lithium comes from. It's like you're just adding it in. 2 LiO, okay. But so Li2O, this can't be right. Okay. On the left side of the arrow there is 1 Li and 2 O. Yeah, on the right side of the arrow there are 2 Li and 1 O. The reaction is not balanced because atoms are not gained or lost in a chemical reaction. The 2 oxygens in O2 cannot be changed since O2 is the formula of oxygen. The 2 lithiums in Li2O cannot be changed since Li2O is the formula of lithium oxide. A big number in front of the symbol changes the number of elements in the formula that follows it. 2 Li means 2 lithium ions. 2 Li2O means 4 lithium ions with, because you can't change it, with 2 oxide ions. Li plus O2. Well, let's just give this a try because I like it when you kind of build up on something. You know, even though you might be wrong, you just kind of build up on the knowledge that you're getting. So let's try this again. So Li is 1 Li plus 2 O, but I don't want to change those. So it's going to be Li1 plus O2 is going to be equal to, now Li2O is the output. So in order to achieve the output, I need to add 2 lithium, and then you've got 2 oxygen. If I add the 2, then it makes this 2. So it's going to be 2 lithium, 2 oxygen. And now we've got 2 plus 2 Li plus 2 O. Now I've got 2O which goes here, Nope. Why do we have 2O? Why do I need 2O? Okay, so I've done something wrong again, that's cool. So a big number in front of the symbol changes the number of elements in the formula that follows it. 2Li means 2 lithium ions. Yep. 2 oxide ions. Oh, I see, but okay, I see. Aha, okay. So although we have 2 oxygen, we haven't changed the original formula. Okay. I wonder what that means mechanically speaking. First, balance for the metal, lithium. There is 1 Li on the left, but 2 Li on the right. So put a 2 before Li on the left. The equation becomes 2Li plus O2 becomes Li2O. Now the equation is balanced for lithium, 2 on each side. The equation is still imbalanced for oxygen. There are 2 on the left and 1 on the right. To get an extra oxygen on the right, we can put a 2 before Li2O. The equation is now balanced for oxygen, 2 on each side. Cool. So let's just try that ourselves. I think I'd like to try another one of these. Okay, let's try again. So let's also get rid of these bad boys. Okay. Sorry, don't know why I said bad boys. These baddies. Right. So we've got 1 lithium. Cool. Easy. And we've got 2 oxygen. 1 Li, and then no, we've got 2 Li, 1 oxygen. Okay, so in order to balance this over, because we've got 2 over here, we need 2 Li. So we're going to say 2 Li, please. And then we've got 1 oxygen over here. We've got 2 here. So in order to get that to 2, I'm going to put the 2 there, and then put the O. Wait. Gosh, I am a dummy. I'm really, really dumb. So it says start with a lithium. Okay, there's 1 Li, but there's 2 over there. In order to get 2, I need to do 2 Li. I've got 1 oxygen, but I've got 2 over here. This supersedes it all, so it's all going to be fine. 2 LiO, that can't be right. 2 Li, 2 Li. Ah, but you can't change that, so it's going to be... Okay, I see. Okay, I need to do a different one as well. So we've got 1 Li on this side, 2 Li on that side. We can't change the equation, so I have to say add a 2 here. So we've got 2 Li. No, I don't understand it. So first balance for the metal. There is 1 Li on the left. Yep. But 2 Li on the right. Yep. So put a 2 before Li on the left to balance it. Okay. Balanced. Lithium is balanced because I've dragged that over to there. Okay. But the equation is still unbalanced for oxygen. So let's have a look at this. I've got 1 oxygen over here, but I've got 2 oxygen over here. There are 2 on the left and 1 on the right. To get an extra option on the right, 1 on the right. Oh, I see. Is it like this? I can't change that, so it has to be 2. Maybe it's that, but it can't be that. It might be this. Okay, let's see what this is. 2 Li2. Okay, so we can put a 2 before Li2O. The equation is now balanced for oxygen, 2 on each side. 2 Li plus O2 equals 2 Li2O. The equation is recheck for lithium. There are 2 Li on the left, but now there are 4 Li on the right. So put a 4 before Li on the left. My God. There's now 4 Li. So you need to go back and forth. God, okay, it's interesting. 4 Li plus O2 is 2 Li2O. Because now I've got 2 oxygen and I've got 2 lithium plus 2. That means I've got 4 lithium plus oxygen 2. That's it. Okay. There are 4 Li with 2 O on the left. There are 4 Li with 2 O on the right. Showing the 4 steps together, we have Li plus O2 equals Li2O, unbalanced for lithium and oxygen. And then I want to do the 2, so I bring this over because I want that one to have 2. And then I've got plus O2, but then I need O2 over here, so I need to add the 2. And now I've got 4 lithium, so I need to go and increase this. Ah, that's amazing. That is amazing. Okay. When we are balancing chemical equations, we first need to know what the symbols and numbers mean. Click here if you are not sure. When we write an equation for a chemical reaction, for example, Mg plus... Yeah, okay. I think I just did that, okay. Example 1 is a reaction between potassium and chlorine. So let's just do this now, because I know how this works now. Cool. Alright, make this a bit smaller. Oh yeah, right, cool. So we got 1K and there's 1K over there, but there's 2 chlorines over here and only 1 here. And I can't change chlorine, so I need to go, so K plus Cl2 KCl2. So now they're balanced, but now I've got 2K. So I need to do 2K over here. 2K plus Cl2 goes to 2KCl. Now I've got 2Ks on each side, but then I have 2 Cls as well because of that. Yeah. On the left side of the arrow there is 1K and 2 Cl. The 2 chlorines in Cl cannot be changed, since Cl2 is the formula of chlorine. On the right side of the arrow there is 1K and 1 Cl. On the right side of the arrow there is 1K and 1 Cl. The reaction is not balanced. Because atoms are not gained or lost in a chemical reaction, the right side needs an extra chlorine. A big number in front of the symbol changes the number of elements in the formula that follows it. 2K means 2 potassium ions. 2Cl2 means 4 chlorine atoms. Two KCl, 2 potassium ions with 2 chlorine ions. To get an extra chlorine on the right side, we can put a 2 before KCl. The equation becomes 2KCl. Now the equation is balanced for chlorine, 2 on each side, but the equation has now become a balance for potassium. There is 1 on the left and 2 on the right. To get an extra potassium on the left, we can put a 2K before it, 2KCl. The equation is now balanced. On the left, there are 2 potassium and 2 chlorines. On the right, 2K plus Cl. 2. Yeah, alright, cool. Showing the 3 steps together, we have, yeah, for example, the reaction of lithium with oxygen. Alright, lithium with oxygen. I think we just done that, right? Yeah, okay, we're circling around now. Cool. Well, that was awesome. So if I go back to this now makes sense. I see. Okay, cool. So let me do that. Whoa. In fact, let me move this down here because I think this is a bit harder, this one. A bit more involved, maybe. So this is balanced because there is 5 carbons, and so there's only one C, so 5 carbons there, and there is an oxygen over here. There's 2 oxygens, in fact. I don't like the color of this. Can I? Oh yeah, now you can see. Cool. So there's 5 carbons, and that's because of that. But that also makes 5 oxygens. 5, 6, 7. So now we have. Let me do a different color. Ooh, that. We've got 2 oxygens, 2 oxygens, but we've also got 8 oxygens, 10 oxygens, 10 oxygen, and so this is 5 oxygens, so 5 plus 7, so this has 10, and this has 7 oxygen. Okay, and then then we have one oxygen over here, which makes, but this is part of H2O, so that can't be changed. And so where does the extra oxygen come from for this? 6 hydrogens, 7, 8 hydrogens, 8 hydrogens, and then you've got 12 hydrogens. So where does these, so 6, 7, 8, then we've got one more, so 7's here, and then we've got, let me read this off a bit. I wonder how to expand this down without to do something weird. I guess it's all about the weirdness. Let's just do that. Okay, and then we've got okay, so we've got 6, 7, 8 hydrogens. 8 hydrogens, there it is, and then we've got 1 O. So one more O. I'm gonna do it like that, I guess. Cool. So now we've got a few missing. This is not balanced, right? So molecular formulae are very usually about the only place where you might come across them is in equations with the combustion of simple hydrocarbons, for example. In cases like this, the bonding in the organic molecule isn't important. That's so interesting. So it doesn't look balanced. This does not look balanced. Hmm. 10 oxygens. There we are. 5 carbons. Let's draw this again. I've confused myself here. This is really weird. Okay. So it's how many oxygens? 10 oxygens. 10 oxygens. And we got 5 carbons. I've got 12 hydrogens. 12 hydrogens. And that's all, folks. Okay. Now on this side we've got 5 carbons. 5 carbons. Okay. And we've got 7 oxygen. Plus 1 6 oxygen plus 6 oxygen. And then we've got how many for hydrogens? We've got 6, 7, 8 hydrogen. 8 hydrogen. Okay, cool. Well, I guess these aren't balanced because in order to balance it, we'd need to start changing this side a bit and start changing this side a bit. So in order to balance this, we would do so I just don't understand. Okay, let me just reread this. So in case like this, the bonding in the organic molecule isn't important. In balanced chemical formulas. So I'm just checking my text here. Okay, cool. Yeah. Right, back to it. If you just write an equation replacing names with formulae, it may not be balanced. The numbers of atoms of each element on the left must be the same as they are on the right. To balance an unbalanced equation, you need to add numbers on the left. Yeah. Okay, well that's BBC. What is an unbalanced formula equation? Equal numbers of each type of atom on the side. It is an unbalanced equation, sometimes called a skeleton equation. This means that there are unequal numbers at least one atom on each side of the arrow. Yep. Just as a matter of principle, let's go and balance this equation. Should be relatively easy. So let's start with carbons then. So our carbons are equal, so this is a tick. No operations required here. However, as we look at the oxygens, we've got too many on the right hand side, so I'll have to add them to this side. So 7 plus 6 is 13. So I guess I can add so 13 so I can add on the left hand side, let me just get rid of these little bits here. This would become, oh well, this would become 1102, like that. And now we are balanced. And then I have too many hydrogens for this, so if I need to add hydrogens, you're going to get, you're going to need 4 more, so there's going to be 10H2O. So now we've got these balanced, but now the oxygens are not balanced anymore because you've got 4 more oxygens. 4 more oxygens, so I need to go back to this site and I'll add 4 more, so it'll be 15. 15O2. Let's make that a little bit easier to move. Okay. So now, let's count these. So the new equation will be C, ooh, don't know that colouring, C5H12 plus 15O2 and 5CO2 plus 10H2O. And let's double check. I think I might have got this wrong actually. I think it's wrong. Almost though. I think I took too many steps. So here is our new equation. And we have, let's go back with this colour, I like that colour. We have 5 carbons. We have 12 hydrogens, and we have 17 oxygen. Yeah, I think I got this wrong. And now we've got 5 carbons, got 7 oxygens, plus 10, 12 hydrogens. Oh, ha! Whoops. Let's get you out of there. Bada bing, bada boom. Hydrogens. We've got 10, 11, 12 hydrogens. Ooh. Ooh. And then we've got, on this one, we've got 10 oxygens. Oh, it's balanced. Yes! Alright. There you go. Haha. Tick, tick, tick. Okay, so this is our balanced version. Now, I'm very interested to know why it doesn't matter. Oh, that's a lovely process. I really enjoyed that. Okay. Why doesn't it matter for that? But let's move on, see if it helps explain that. A molecular formula simply counts the numbers of each sort of atom present in the molecule, but tells you nothing about the way they join together. For example, the molecular formula of butane is C4H10, the molecular formula of ethanol is C2H60. Oh, sorry. Molecular formulae are very rarely used in organic chemistry because they don't give any useful information about the bonding in the molecule. About the only place where you might come across them is in equations for the combustion of simple hydrocarbons, for example. That, in cases like this, the bonding in the organic molecule isn't important. So why do we need to balance chemical equations? Reactions must be balanced to satisfy the law of conservation of matter that states that matter cannot be produced or destroyed. The law of conservation. So this is probably pre-running it, I guess. I don't know. I don't know why it's unbalanced. I don't know what they're trying to say here. Very interesting. Bear with me. Just gonna do a blood test for my diabetes. Sorry, I can't bother to stop it all, but let's take a few moments. Sorry. I think I was a bit high before I started this. But I had an injection, so I wonder if yeah, it's going down slightly. Okay, that's good. Cool. And it's 12:04 UK, so let me do my long-term injection for nighttime. So it starts working away. I'm gonna go to bed on 10 units. Alright. How long have we been doing this? Oh, an hour 30. Gosh. Time goes very quick when you're having fun, that's for sure. Alright, cool. Let's move on. I'm liking this document so far. It's making me ask questions. Structural formulae. A structural formula shows how the various atoms are bonded. There are various ways of drawing this, and you will need to be familiar with all of them. Well, start with the positive, why don't you? A displayed formula shows all the bonds in the molecule as individual lines. Okay, and we get that. We already get that. You need to remember that each line represents a pair of shared electrons. Now, let's just visualize that. Let's just visualize that. And I'm going to call this balancing equations. And we'll go new page. Right. So when I'm thinking of the structure of a chemical, of an atom, sorry. To remember each line represents a pair of shared electrons. Oh no, go back. So if I had an electron, oh let's go different color, electron here, and an electron here, and we'll have a proton here. Ooh, protons, electrons, protons. Protons are negatively charged particles. Electron negative. Okay, my apologies. Try this again. It's good to. So I'm so glad I'm drawing it. Ha! So negative, negative. So positive, positive. I think that makes a lot of sense actually. Then we're going to have those neutrons here. And so this happens like that. And it says you need to remember that each line represents a pair of shared electrons. So let's imagine I have exactly the same atom next to this. Oh, that's not what I wanted. Do it again. Okay. maybe I can draw a bit more fancy. These are going to be the sharing. Let's go purple. So this equals a bond. That can't be right because they're both negative. They won't attract each other. Each line represents a pair of shared electrons. For example, that is wrong. This is wrong. That is not how that works. It must be that the proton does that. And in fact, let's just, can I rotate this? Would that go on? That would be awesome if I could rotate it. Rotate. Rotate left by 90. Alright, let's do that then. So I'm assuming that that's how that bond gets made. But it says a shared. The displayed formula shows all the bonds in the molecule as individual lines. In the molecule can be made up of many atoms. How many atoms in a molecule? Group of 2 or more atoms held together by chemical bonds. Okay, this makes sense. Haha, that's awesome. You need to remember that each line represents a pair of shared electrons. For example, this is a model of methane together with its displayed formula. Notice that the way the methane is drawn bears no sorry, this is wrong. Let me just make sure we know this is wrong. Because I'll forget to update then. I'll be like, oh, that's how it works. Notice that the way the methane is drawn bears no resemblance to the actual shape of the molecule. Methane isn't flat with 90 degrees bond angles. The mismatch between what you draw and what the molecule actually looks like can lead to problems if you aren't careful. Okay, that makes sense. For example, consider the simple molecule with the molecular formula CH2Cl2. You might think that there were 2 different ways of arranging these atoms if you drew a displayed formula. CH2Cl2, so they're going C in the middle, and there's 2 of them. So let's imagine that's the 2, and then you've got the single one over here. The single one is bound to 2 hydrogens. That's why that looks like that. And then you've got the chlorine is bound to the CH2. The chlorines are bound to the CH2. But it also could be one hydrogen is bound to the carbon, but there are 2 hydrogens bound to the carbon, so that's why they're bound like this. And then the CH2 is bound to the chlorine. So the CH2 is bound to the chlorine, which has 2. The chlorines could be opposite each other or at right angles to each other, but these 2 structures are actually exactly the same. Look how they appear as models. Capture the top hydrogen and rotate the molecule a bit. One structure is in reality a simple rotation of the other one. Yeah. Note, this is all much easier to understand if you have actually got some models to play with. If your school or college hasn't given you the opportunity to play around with molecular models in the early stages of your organic chemistry course, you might consider getting hold of a cheap set. The models made by Molybod are both cheap and easy to use. An introductory organic set is more than adequate. Google Molymod to find a supplier and more about them. Share the costs with friends, keep it in good blah blah blah. Okay, consider a slightly more complicated molecule. C2H5Cl, so that's 2 chlorines, 5 hydrogens and 1 chlorine. 2 carbons, 5 hydrogens and 1 chlorine. The displayed formula could be written as either of these. I wonder what H5 is. What is H5? Chemical. Cyclopentanediol, maybe. Cyclopentanediol? Dienol? Oh god, I don't like these things. Yeah, C2. Okay, so C2 would be the two carbons here, and they're bound to 5 hydrogens. 1, 2, 3, 4, 5. Okay, and the chlorine gets whacked on the end. But it could also be shown as 1, 2, 3, 4, 5. Okay, but again, these are exactly the same. Look at the models. The commonest way, the most common way to draw structural formulae for anything other than most. Oh, I need to blow my nose. Sorry about that. So the most common way to draw structural formula for anything other than the most simple molecules, drawing a fully displayed formula is a bit of a bother, especially all the carbon-hydrogen bonds. You can simplify the formula by writing, for example, CH3 or CH2 instead of showing all these bonds. Makes sense. So for example, ethanoic acid ethanoic acid would be shown in a fully displayed form and a simplified form as, so ethanoic acid, ethanoic acid is going to have something like CH3, so C2H3 O2H. So this will be something like C2H3 O. I think it'll actually be H3 C2 O2 and the H, and that will be the H is only bound to 1, and the carbon is bound to 2 C's, so this is bound to the 1 oxygen. And then you've got the other oxygen bound to the H. Oi, oi, oi. C2 O O2H? Is that really right? It can't be. Well, this is my understanding because I don't know what this double thing means. And let's go and have a look. Ethanoic acid. Ethanoic acid formula. Oh god, I put an H on the end, an R on the end. Haha. CH3. Okay. Let's go back to this. So they've got CH3. Let's just start with that and see if I can rework what I've gone wrong on. So apparently it should be CH3. What was that again? Yeah. So C bound to 3H. Oh, it's what I started with. No, it's not. Ha. And then you're going to have C bound to O, and then O bound to H, and the O's are bound. Is that right? Yeah, cool, okay. Cool. Also written as CH3 CO2H. Okay, yeah, these all make sense. C2, yep. C2, H4. Oh yeah, I guess it doesn't matter. O2. It just doesn't matter. That is amazing. Wow. Okay, I did not know that. That's very interesting. Um, and this one, yeah, okay. CH3, yeah. Oh, excuse me. How much have we got? Oh god, I'm nearly at 2 hours. Okay, you could even condense it further to CH3COOH. And would probably do this if you had to write a simple chemical equation involving ethanoic acid. You do, however, lose something by condensing the acid group in this way, because you can't immediately see how the bonding works. Yeah. You still have to be careful when drawing structures in this way. Remember from above that these two structures both represent the same molecule. The next three structures all represent butane. Yeah. All of these are just versions of 4 carbon atoms joined up in a line. The only difference is that there has been some rotation about some of the carbon to carbon bonds. You can see this in a couple of models. Molecules twisted about this CC bond. Not one of the structural formulae accurately represents the shape of butane. The convention is that we draw it with all the carbon atoms in a straight line, as in the first of the structures above. This is even more important when you start to have branched chains of carbon atoms. The following structures again all represent the same molecule, 2-methylbutane. Branched chains of carbon atoms. Okay. The two structures on the left are very obviously the same. Yeah. CH3 links to CH. You've got the CH3 here. Ooh, okay. Got the CH3. Ah, related to CH and the CH2 related to the CH3, I see. The other one isn't so obvious until we look at the structure in detail. So you've got the CH3 is related to the CH2, and the CH is related to the CH3 and also to the CH3 here. Oh, fair enough. There are 4 carbons joined up in a row with a CH3 group attached to the next to end one. That's exactly the same as the other two structures. If you had a model, the only difference between these two diagrams is that you have rotated some of the bonds and turned the model around a bit. To overcome this possible confusion, the convention is that you always look for the longest possible chain of carbon atoms and then draw it horizontally. Anything else is simply hung off of that chain. It doesn't matter in the least whether you draw any side groups pointing up or down. All of the following represent exactly the same molecule. Let's let's take that. That's good. So this is a bit of a bath, but let me just name this. I don't know. Doodle notes, and then we'll call this a new page. Let's call this learning structural skeleton formulae. I like a good picture as well. It doesn't. So longest possible chain of carbons, and then draw it horizontally. It doesn't matter in the least whether you draw any side groups pointing up or down, okay? If you made a model of one of them, you could turn it into any other one simply by rotating one or more of the carbon-carbon bonds. If you made a model of one of them, you could turn it in any other way. But tired now. If you made a model of one of them, you could turn it into any other one simply by rotating one or more of the carbon-carbon bonds. Okay, this is what I wanted to learn, this part. How to draw structural formulae in 3 dimensions. Well, I have to say, I am quite tired. And I see this goes on a bit more. I'd like to give it the kind of full dedication it deserves. So let's stop it here. And it'll be good for revision as well, because I can recap. So in episode 8, where did we get? We were looking at this site. We got to here. Okay, cool. That was good, actually. I've learned a lot. I didn't know about the balance of an equation, and I certainly feel like I've got that down. That was very fun to figure this one out. And it looks like we're just about to eke into the actual cool structural stuff. So, good learning. So, yeah, and keep loving, keep learning. Speak to you later, guys.